Our goal for this project was to create a full-stack system for stylized robotic drawing of 3D models, incorporating fine details through an enhanced perception system and the ability to wield varying strokes. We wanted to combine the creativity and expressiveness of art with advanced robotic technology. This was challenging because it required advanced perception techniques, creating precise trajectories, and mapping varying line widths to nuanced robot movements. Our methodology consisted of 3 main components. The first was extracting contours through image-to-sketch simplification. Next was drawing trajectories from vectorized sketches. And last was fine-tuning the robot's motion in the z-axis to create varying stroke widths. Our image processing pipeline consists of 5 steps. First, we capture an image of the bunny in the scene. Next, we use a model to transform the image into a sketch. Then, we use another model to extract simplified contours from the sketch. Once we have the simplified contours, we convert the raster image into a scalable vector graphics image. Lastly, we skeletonize the contours from the SVG image using the medial axis transform.
Now we face the task of downsampling and separating the join lines. Our initial skeleton output consists of over 5,000 segments. To streamline this complexity, we filter out the moot points and downsample them for the key join frames, striking a balance between preserving smoothness and reducing the total number of frames. We then separated these points into distinct join lines to ensure that they align with the sketch's intent. By analyzing the rate of change in distances between consecutive points, we generate a sequence of lists, each representing the trajectory for a specific join line. Next, we have the target join trajectory. Before it's given to our controller, each was augmented with a pre-draw and post-draw pose by lifting up between and after each join line. We use differential inverse kinematics to control for the desired trajectory from the keyframe poses. At this step, we only have constant z-axis coordinates, so the panner is basically plainly drawing on the canvas.
In our efforts to artistically enhance Sketchbot's drawing abilities, we embedded the ability to dynamically change the stroke width of the rendered drawing. To achieve the dynamic stroke width, we used the spatial force applied on the canvas by the chalk at the centroid point. We then calculate the magnitude of the scaling force and apply a constant scaling factor. This value is then mapped to the width of the line at the specific contact point, and in this way, we are able to dynamically vary the stroke width based on the hydroelastic contact between the canvas and the chalk. Our solution for where to vary strokes was inspired by the dynamic nuances of brush strokes on a canvas. To mirror these expressive strokes, our solution calculates the curvature of line segments generated for the drawing, utilizing the Menger curvature calculation. We extract the areas of high curvature by looking at the mean of the normal distribution and taking points 1 standard deviation above and below the mean to represent our points of, quote, high curvature. Then those points are mapped to areas where the robot's chalk will penetrate deeper into the canvas by decreasing the z-value and thus ultimately generating a wider stroke due to the contact force. During our iterative process, we found that abruptly changing the z-value generates a choppy drawing that does not mirror the gradual change in stroke one sees with a paintbrush on a canvas. Thus, we worked through several iterations of modifying z-values before and after to gradually place force and generate a more natural-looking stroke. Our final solution included a linear decrease then increase across 3 neighboring points on each side of the point of high curvature. The solution generated smoother stroke changes and mimicked the stroke of a paintbrush on a canvas more naturally. Our approach has 3 key steps: image-to-sketch simplification, utilizing open-source models to create contour images suitable for drawing, vectorizing contours and generating optimal trajectories for drawing, followed by the mapping and fine-tuning the robot's motion in the z-axis to create varying stroke widths throughout the drawing.